Hi, in this video we're going to go over section 10.1 on parametric equations. So imagine that you have a particle that is moving along a certain curve, like what I'm showing here in this figure. So you cannot describe the curve C by an equation or from the shape y equals f of x or a function, because it will just fail the vertical line test. When you put a vertical line here, then that vertical line will touch more than one point, and I cannot describe this as a function. Still, if I can just write the coordinates x and y, I can think of each of the coordinates x and y as a function that is going to come from the time, or a parameter t, and describe each of the coordinates as x equals f of t and g equals g equals g of t. This pair of equations that we have here is often a good way to describe a curve. Now, if we have these functions in terms of a third variable, we're going to call that third variable a parameter. And so when we describe x equals f of t and y equals g of t, we call this equation parametric equations. And each value that we give of t is going to determine a particular point xy that we can plot, of course, in the coordinate plane. Now, when t varies, the point xy given by f of t, g of t, also varies and traces out the curve, which is what we call the parametric curve. But the parameter t is not necessarily going to represent time. Sometimes you can use theta, and it can represent angles, or you can use multiple letters that are going to represent different things. Sometimes t will denote time, and in that particular case we can interpret the curves xy equals f of t, g of t as the position of a moving object at the time. Now let's take a look at an example. So let's first try to sketch and identify the curve that is defined by these parametric equations. So let's go here to the board for a second and give some values that we can use. So the first thing is that, of course, we want to describe everything in terms of the parameters. So we're going to start by giving t, and of course we're going to get x and y. Dependent of some curves, you're going to have certain values for the parameter given, but if not, you can assume that you can use whatever values you can. So for example, here we can start with t equals 0, and so if t equals 0, then you can plug in x, and so that will be 0 squared minus 2 times 0, right? So at t equals 0, you have 0 squared minus 2 times 0 for x. And so this will be 0, of course. And for y, you will have 0 plus 1, and so that will give me a 1 here. We can continue giving values that way. We can give 1. And so at 1, at t equals 1, then you have that x is equals 1 squared minus 2. And so that's going to be 1 minus 2 is going to be minus 1. And y is going to be 1 plus 1, which is going to be 2. So we have minus 1, 2. And then at 2, then we have 4 minus 4. So we get, again, 0. And with 2 and y, we get 3, so on and so forth. And this is the way how we construct the curve in general. So let's go with 3 and 4. And notice that I'm just giving positive values here. Imagining that this t might be some time, but there's no reason why I cannot give negative values. So if I plug 3, I get 9 minus 6, which is 3. And if I plug then 3 in here, I'm going to get 4. And of course in 4 I'm going to get 5. And in 4 for this I'm going to get 16 minus 8, so it's going to be 8. So now I have this particular table. And then I can try to plot that on the plane. And the way that you will plot that on the plane is by marking the points. So you're going to have here the x-axis, the y-axis. And so what you mark are these particular points. So for x equals 0, then you're going to mark y equals 1. So this is the point that you're marking. For x equals minus 1, which will be here, then you're going to have that y is equals 2. So you're marking this point here. For, again, x equals 0, now you're going to have 3. So you also have this 3 here. This is 3, 2, 1. And so we're going to have this. And so you start to see how the repetition of these points happens, and that you might have that this is joining these points in this way. So that's your intuition when you start going in there. Of course, in x equals 3, then we have 4. So we can go 1, 2, 3. And so 3 is going to be 4 here. And when x is equals 8, error here, then we're going to have that this is 5. And then we can kind of see the trace of how things are going. And we can kind of guess that this is going to have the similar behavior down here. And this is how the curve is going to be described. So now we can actually take a look of some extra points in there. So this will be how this curve will come into place. Here I'm having some extra values. I'm using -2, -1, and so you can see that I can also get the values for negative y down here. And so this is the shape that you get. Notice that we're putting the points on the plane, and after putting the points in the plane, then I can establish how am I going to join that. And of course, because we're going on the direction of t, then the direction of the curve is, think about how we go from negative numbers to positive numbers, or from the lowest numbers to the biggest number. So notice that we start by t equals -2, and we go in the direction of t positive. So here t equals -1, t equals 0, and so the curve is guided by that direction. Now, the parameter that we have here, t, is just a way of having an extra relationship for the variables x and y. But of course, this is a parameter, and most of the times we're going to be able to eliminate that parameter and put this x in terms of y, or y in terms of x. The result is not going to be a function, but we're going to be able to eliminate the parameter and just put a relationship of x in terms of y. And that's precisely what happens here. So we assume that y equals t plus 1. We start with x being t squared minus 2t. And so we're going to fold this so we can try and get t plus 1 in bold, or from just subtracting here, y minus 1 is equals t. And so if y minus 1 is equals t, I can replace t by y minus 1. And so now I get that x is just y minus 1 squared minus 2 times y minus 1. And then I can break this apart, and this is going to give me x is equals y squared minus 4y plus 3. So in that way, I'm get rid of the parameter and finding an expression that I can also use in a different way for making calculations, classical calculations like derivatives and some other things. Now, since the equation x equals y squared minus 4y plus 3 is satisfied by all this pair of points that we have here, then we can use that to describe this parabola that we have over here. Now, sometimes we can restrict t and not take all the numbers, but just take it to lie in a finite interval. And so if we take the examples that we have from before, we have that x equals t squared minus 2t and y equals t plus 1 with t between 0 and 4. It's just going to give me some of those points that we have from before. So if I plot the points that I obtain, you can notice that now it's only giving me this piece of the curve. That kind of matches with what I was doing here, except that I can't remove this piece that I have over here. And so that's now going to match with what I did here and it's just this piece of the curve. Now, notice that this is exactly the same parabola that we had before, but we're just cutting pieces, and now start at 0.1 and it's going to end at 8.5. This is valid for describing particular curves. Now, we can do this with some other different things, and there are multiple ways of representing this on whether it's computers, calculators, of the such. So for example, we can use that, and using a graphing tool like, for example, the Desmos calculator, you can go ahead and plot that, and you can use the parameter that you have. So for example, if I had cosine and I want theta, so I can establish the cosine of theta, and then sine of theta is y. So sine of theta. Okay. And then here I'm gonna specify where theta is going for. I can here's the set slider. Okay. Let me just put H here instead. And so this helps me out writing the curving here, although this doesn't seem to be working. I'm trying to just, there we go. If I use T shows up, I'm gonna write 0 to pi, or 2 pi, and so now it's gonna match my circle here. This probably is something that you already know, that x equals cosine, y equals sine, represents the unit circle of radius 1 when you make t move between 0 and 2 pi. And so this is another example of a parametric curve. Of course, in this case, our parameter is t, and t is moving between 0 and 2 pi. There are multiple tools that you can use to get this plot, either GeoGebra, Desmos calculator, or even your own calculator sometimes. Again, you're going in the direction of t, and so in that way you notice that when you start 0, you get into 0.10, then this moves to, if you go, let's say pi half, it moves in this direction, then goes to pi, then it goes to 3 pi half, then it goes to 2 pi. So it does this orientation, and that orientation comes in terms of where the points are being acquired according to what the output that you get with the t. Okay. Now notice that here we're moving around the circle counterclockwise with this direction, but you can also probably find another interval where you can make it go clockwise, or you can make it start from a different point. So for example, you make t start from minus pi half to pi half, then you can cover from here to here, or you can even try a negative direction, in which case you go in this direction to complete the circle. So the parameter t and the values that you get with the parameter t for x and y is what determine the direction of the curve. Now let's use a graphing tool again to get some of this curves plot. So we had this before. We had this circle here, and this was a good example. But let's say we can match this out. For example, we have x is equals y to the 4 minus 3y squared. And so you notice that this is the curve that we have over here. And so notice that now we're actually going to see that we can have the same, but with the parameters. Notice that this is describing x equals y to the 4 minus 3y squared. So this means that x is a variable that is in terms of the parameter, or is a dependent variable. So we can write t to the 4 minus 3t squared, and then just give t as the value for the parameter. And so we can go like minus 4 to 4, and notice that it's going to cover exactly the same part that this curve is doing. So we have x equals y to the 4 minus 3y squared, and this is actually covered by the same thing. This is because both of these representations are the same. I'm given y as the parameter. I'm saying y is equals t, and y is going to represent my parameter. And now because x is being described in terms of y, then I can get the parametric equations x equals t to the 4 minus 3t squared and y equals t to represent my curve. Now, some other different expressions can be more complicated or simple depending on what we have. So for example, for the last curve that we have over here, we have a plus cosine of t, and notice that we can add sliders for a and t. So we do that so we can have different movements, and this is now going to show things in here. Let me just remove this so I can just have this in there. Because that slider is also changing values for this. Now I'm going to go with y being a tangent of t plus sine of t. And so now you can see the point here. So this is t equals 1. But if I move the point, then you can kind of see how this is moving along the different places. Now we simply remove the parameter. Let's say we remove the parameter here and we just put a 1 or let's say a 2 on this, and then we fix the interval that we want to use, then we're actually going to get the full curve. So just take into account if you're going to be using the sliders or you're going to be using a full interval to just try and find out how the curve actually looks. Of course, remember that in this case a was another parameter, so the more that you play with the value that was in the parameter, the more that you're gonna get difference on the graph that you had over here. Okay, so that's overall the difference between just having a particular parameter or having more than one parameter with different sliders. Notice what the situation is once I actually go ahead and just move t between 0 and 2 pi, but I make everything on the other parameter moves. That's going to completely change each of the curves and the points that I'm obtaining. So at a certain point, I even seems like I get a circle. Notice with ax equals 0, this tangent goes away and this becomes a circle. So depending on the number of parameters that you have involved, you have difference on your curves. Okay, so for the most part, we're going to be managing a single parameter here, and Desmos is an excellent tool to just get to play with how these curves are going to look like. Now in section 10.2, we're actually going to see how to make some calculus with these curves and what can we do in terms of the things that we know before. This includes limits and differentiation and integration.